Quantum physics is a fascinating subject. It studies these small particles that sometimes behave like waves, these objects that can be in multiple states at the same time, and it has these laws that seem to defy understanding. And yet, this field is quietly underlying a lot of the technologies that we take for granted today. Things like lasers, the GPS that we might have used to get here, and even the processors that are inside the phones that we all have in our pockets would not be possible if we did not understand deeply how this realm of quantum physics works. However, there's this new upcoming technology that is quietly progressing in the background that is all about quantum physics, and that is quantum computation. And this is what I want to talk about today a little bit, about quantum computing and how it has been changing a little bit how the world works slowly and how we feel like this will be ramped up in the next few years. My name is Sergi Ramos, and quantum computing has also changed me in a personal level. I would not be here if it was not for the advances in this field that have happened in the last 10 to 20 years. So hopefully by the end of my talk, I have been able to share a little bit of my excitement for the field. And that next time that you might open an article on quantum computing, you feel a little bit closer to the subject than you do right now. So let's start with maybe an obvious question, maybe a question that someone in the audience might have, is, do we actually need these quantum computers? Are our regular computers that we use every day not good enough? Well, the answer is a little bit tricky. I mean, the computers we use are amazing. Like, we are doing calculation after calculation at impressive speeds, new breakthroughs in applications and AI are coming out every day. But there's an uncomfortable truth behind that. There are some problems that we know, and by that I mean we mathematically know, that classical computers can only get us so far. These problems are also not fringe problems. They appear constantly in fields like cryptography, in chemistry, in optimization, and these are problems that people face every day. We know that some of these problems would take an extremely large amount of time to solve on a classical device. That is not cause for alarm. That doesn't mean that we have to throw all of our computers away. Actually, we like that some problems are hard to solve. For example, our cryptography system, the way that we protect our secrets while we share information with each other, is based around some problems that are hard to solve. A small example, if I take two prime numbers and multiply them together, and I give you the result, without my original two numbers, you would not be able to find the numbers that I'm keeping without spending around the time that the universe has been advancing. This is good because then I can use them as a key to keep my information private. This is good, but this is one of the avenues of attack that quantum computers can do. Quantum computers, for example, can solve this problem in a much faster way than classical computers do. So, are these computers just much faster and more advanced classical computers, or are they something entirely different? And what I will try to put forward today is that these are computers that work under an entirely different set of laws. We use the basis of this quantum physics to do computation, to encode information and to process it in a different way. There's essentially three main ideas behind this process. The first one is what we call superposition. So we, as classical beings, we usually follow one path at a time. We take step by step until we reach our destination. Classical computers do the same. We follow one computation, we do one step after the other, and we can only do the next step once we know what has happened before. Quantum computers do not need to do that. We can keep in a quantum superposition multiple paths at once, and then when our quantum computer will perform an operation, it will happen to all of them at the same time. There's a catch, though. If we want to extract information out of this device, we have to bring this quantum information out into our classical world. This comes with the catch that only one of these paths will be able to be output at the end. That seems bad, right? We want to use all of these paths at the same time, but we only can extract one, so how can we go about that? That's where the next two ideas come in. These are called entanglement and interference. First of all, these quantum paths have a very particular property. When they get close together and they interact, even if we take them apart, they will keep some information from that interaction in their very being. Suddenly, these multitudes of paths cannot be described anymore by explaining each one of them separately. We need to treat them as a whole being. And not only that, but these paths can interact with each other in a very special way. Paths that agree might reinforce each other and boost the outcome, and paths that disagree might completely cancel each other out. So by doing this orchestration of performing actions in superposition while containing full information and canceling out all of the wrong outputs, we can make it so by the end of the computation, only the right output is the correct one. If that sounds tricky, it's because it is, and it's also really subtle. But it's one of the main driving forces and one of the main interesting parts of quantum computation. So we know a bit how it works. The next question we should tackle is, how can we build these machines? We have computers on our desktop, we have computers on our phones, but how can a computer work under these circumstances? Well, it might be surprising that the answer is that we can build these things, and also that we can build them in entirely different ways. For example, one way that we could go about is to go to the quintessential quantum particle. Atoms, which are these small particles that make up all matter, behave quantum mechanically. And with laser pulses and magnetic fields, we can control them in a very precise way. We can bring a lot of them together, we can bring them close, we can take them apart, and we can do quantum computation with them. But we can even go a step further. We can forego these small quantum particles that nature gives us and build our own. We can put very small circuits made of aluminum, and if we bring them to extremely low temperature, quantum phenomena starts to appear. And with the right engineering, we can make these small aluminum circuits made out of millions of atoms to behave like a single artificial atom. These different technologies are related, but they use completely different machines. But they all have the same goal of quantum computation. And these are being developed all around the world, and even here in Singapore, there's efforts to build all of these technologies. This process of understanding, building, and operating these machines is not trivial. It needs a large amount of infrastructure, it needs education, it needs mentors to go through young scientists to get them to this point, and it needs an ecosystem that values long-term knowledge before short-term returns. I, for one, have been extremely privileged to be able to grow into such an environment. And this environment is something that countries all around the world are trying to embrace. Indeed, this quantum technology is becoming more and more something of a strategic resource. Being able to know what's going on in this field, how it will affect cryptography, how it can affect drug discovery, is something that countries are pushing to understand. We all don't want to be just consumers of quantum technology, but we want to embrace it and we want to contribute to it ourselves. And this requires the building of an environment to bring together both scientists and educators, also policymakers and infrastructure, to make sure that this science, which is a collective effort, can be done properly. And I'm part of a very vibrant ecosystem here in Singapore that we're working towards that exactly. And I think ecosystem is a very important word here. Science is indeed a collective effort. This romantic idea of a scientist shut in their office, working away at a problem by themselves is but a relic of the past. Now, scientific progress happens in collaboration, it happens in discussion with peers from different fields, from different institutions, and even across borders. And this spread of knowledge, this idea of open science, of science as an open field that everyone, regardless of their background, can contribute and be a part of, I think that's key to advances. And by advances, I mean small advances and even breakthroughs. I feel like all advances regardless of how small they are important and should be pursued. And it is this collaboration in this global effort and the sharing of knowledge that we can also help bridge a little bit of the barriers that might be between different fields, between different countries, and between different backgrounds. So, after talking a little bit about this, I have maybe danced around a little bit maybe the most important question, which is, okay, we know now how quantum computers work, we know a little bit how to build them, but what do we actually do with them? Do we already know what these machines will be good for? And to that, there's two answers, one short and one long one. The short one is that we already know some algorithms that we know for sure a quantum computer can help us. The factorization problem that I posed at the beginning is one of them. It's just that the machines that we have nowadays, technological marvels that they are still not there to solve problems at a large enough scale. But I feel like a bit of a longer answer might be a bit more interesting for this talk, which is we are building algorithms, we are thinking of problems to be solved with a machine that we do not have yet access to. And that makes it so that the quantum algorithms that we know we will work are strikingly small. This might not come as a surprise, as we are trying to build these protocols for a machine that we don't have access to. We are just projecting ahead. And that's where now is an extremely interesting time to be part of this development. These machines are slowly, in these years, going to be much and much better. And maybe more importantly, they are starting to be available to a large global community of eager scientists that are going to explore this computation landscape to see what we can find. This is a new and exciting thing, and I feel like now and in the next few years we're going to see amazing things as both the theory and the devices come together and work together in this open science environment that we have set up. So hopefully, after listening to me for these minutes, you now have maybe a bit more of an understanding of quantum, and maybe you are a bit more excited to see in the next few years what comes out from this fascinating field. And maybe even some of you in the audience will join us in exploring this exciting landscape that is going to be available soon to all of us. Thank you.